Hello friends, me and Arthur are going to go over the last part of the test for you. So this last part was built to be um, more like the free response section on an AP test. So you've got a lot of parts to every question. So we're given an f. It is defined to be square root of x plus 1 when x is between 0 and 3. And it's 5 minus x when it's between 3 and 5. And it asks, is f a continuous function? So the way we're going to test the continuous function, we don't really need to test whether it's defined at that point. So, 3 equals 1, square root of that is going to be 2, so it exists at that point. So we need to figure out the limits. So the limit as x goes to, first thing, this function is continuous as long as x is greater than 0. So that's fine. And this function is continuous everywhere. So if we're looking to see whether f, the combination of these two, is a continuous, we need to basically look at where they join, which is at 3. So we are going to take the limit of f as x goes to 3 from the negative side, which is going to be where, if we're going from the negative side, we use this definition. So that's the square root of 3 plus 1, which is the square root of 4, which is 2. And then we're going to look at the limit as x goes to 3 from the positive side of f of x. If you're coming from the positive side, you need to use the other definition. So that's going to be 5 minus 3, which is also 2. And since these limits are equal, and we know that it's defined there, we can say that it is a continuous function. At x equals 3, so it's continuous right there. Everywhere it's defined. Whenever you see explain, you want to use at least a few words. Obviously, since we're here, I didn't use full sentences. Maybe do that on the actual test, but you can just, as long as you're saying like, oh, we use we show both limits, definition of continuity at that one point, and then making sure to note that these are continuous on their own domains. All right, now for part B, we have another function defined by this for k's and m's and all sorts of stuff, right? Where it's given that k and m are constants. So it tells us that g is differentiable on the interval from 0 to 5 and asks what k and m are. So this seems like it's not enough information until you realize that to be differentiable, you also have to be continuous. So because it's differentiable, we know that g is continuous. So we know that the limit as x goes to 3 from the positive side of g of x is equal to the limit as x goes to 3 from the negative side of g of x, which means that k times the square root of 3 plus 1 has to be equal to m times 3 plus 2. So on the other side of this function, so we know that 2k equals 3m plus 2. So this is one bit of information. So that's just using continuity. We haven't even used the full string of differentiability. So differentiability, roughly speaking, would say that the limit of the derivative in prime of x is the same as both sides. Now, if you do that on this side, the positive side, g prime is just n everywhere, including at 3. Derivative of that, so we've got k times 1 half, so derivative of square root, 1 over 2 square root of x plus 1, except x is 3. So that, 2.4, square root of 4 is 2, so we know that n equals k over 4. Alright, so however you want to do a substitution would probably be appropriate here. If this is the case, I'm going to work in whole numbers instead of fractions, just to start. That means 4n equals k, which means over here we have 2 times 4n, 8n equals 3 plus 2, which means that 5n equals 2, and equals 2/5. And then we can use, honestly, whichever equation we want. But probably this one, it's easier. So 4 times 2/5 equals k, which means that k equals 8/5. And there you go. Keep in mind, so the linchpin of this is that differentiable, whenever something is stated to be differentiable, that's actually telling you two things, because differentiability, you need to be continuous. So you use the information from continuity and the information from differentiability to solve that one. Alright, so now we got a new one. Let f be a function where f prime of x is equal to x times the square root of f of x. Already this is kind of weird, but we'll roll with it. And f of 3 is 25, and I want f double prime 3. Alright, well, this is kind of weird, but we can get to it. Just, again, be kind of like very direct, and if you don't understand, it's not like, don't understand the whole thing, it's no big deal to start off with. Just kind of play along with how it should work. Of course, f double prime, that's the derivative of the derivative. So we're going to use this and take the derivative of this side. Well, this is a straightforward product rule kind of thing. So it's the first times the derivative of the second. So we're going to have 1 over 2 square root f of x, and then we're going to use the chain rule, so it's going to be f prime of x. And then, product rule, we have to say plus the second square root of f x times the derivative of the first, which is just 1. At this point, you might want to recognize that you can use this definition again right here. So we have x times 1 is x. X times f prime of x is f square root of f of x over 2 square root of f of x. And you see immediately the benefit of doing that is that these will cancel right out, which is nice. Plus square root of f of x. Now we want f double prime of 3, so we get 3 squared, so 9 over 2, plus square root of f of x. Well, we tell us that f of 3 is 25, so this becomes 9 halves plus square root of 25 is just 5. However you want to simplify that, probably I would do it as an improper fraction. That's going to be 19 halves. That's all there really is to that one. Just as long as you remember the square root, however you remember that. Moving on. we have a situation. We were given for a function with behavior consistent with the following chart, all of this stuff. Find all relative extrema. Okay, so extrema is our fancy word for mins and maxes. So we are looking for, wherever this is. We can think of, we're going to look at the derivative for that. And don't think function with behavior consistent. It doesn't really tell us anything about whether the function is defined of less than 0, and it doesn't certainly tell us anything about anything at 4. So it's up to you whether you want to count, or from my position, it's up to you whether you want to count this, since it's whether you want to count this as a relative min. Probably wouldn't, since technically if it were n, like these wouldn't be defined. So probably not that one. For extrema, we're going to look at critical points, which are where the derivative is 0 or it does not exist. Alright, so we've got critical point at 1, critical point at 2. So at x equals 1, well, what's going on at 1? Well, the derivative is positive on one side and positive on the other. That's not even an extremum, that's a inflection point. Which again you can tell because the second derivative is equal to 0. So, alright, cool. Derivative isn't defined at 2, but it does go from positive to negative. So you probably have something like that with a corner here. But in any case, positive to negative, so you have at x equals 2, you have a relative maximum. And that's really the only one we've got. Alright, moving right along. Sketch a potential graph. Sketches. Alright. Of the function, the good news is that they provide values for f of x. So we're going to sketch our graph. It goes from 0, 1, 2, 3, 4. 1, 2, 3, 4. No big deal. We have f of x is going to be start at -1. It's going to go up to 0. It's going to go up to 2. It's going to go back down to 0. And then that's all the things from our f information. So now we're going to use, to decide how we connect these, we look at our derivatives and our second derivatives. So from here to here, positive, so it's increasing, but the curvature, f double prime, is negative. So we need to have increasing but negative curvature. So we need something like this. Alright? So you see how it's increasing, but the curvature is pointed down. And moving to this region, we've got positive first derivative, positive second derivative. So the curvature changes so that it's like that. Great. Now, in this region, hopefully it's familiar, we have a decreasing function with a negative curvature. So that's a concave down. So we're going to start with it not decreasing by very much, just make it kind of a step. And curve down. Then for our last region, it's negative, so it's still decreasing, but the curvature is positive. So as we curve down, once we hit here, we're going to start curving back up again, but it's still decreasing for as far as we know. And then it isn't defined at 4, so we won't worry too much about what to do. But yeah, plot all the points that are given, and then connect them how you know they have to look based on the first derivative and the second derivative. Alright, so Now we have a function with values according to the following table. Everyone wants tables, right? We have f and g, they're everywhere differentiable, and g is strictly increasing, which you can see with 2, 3, 4, 6. And h of x equals f of g of x minus 6. Explain why there must be a value r to run through so that h of r equals -4. Guarantees of this with h, that's probably an intermediate value theorem kind of thing, which, well, we're going to test. What is h of 1? Well, that's going to be f of g of 1 minus 6. G of 1 is 2, plus 2 is 9. That's going to be 9 minus 6, which is 3. Now we're going to do h of 3, which is f of g of 3 minus 6. So g of 3 is 4, f of 4 is -1, so -1 minus 6 is -7. So by intermediate value theorem, there must be some r. So h of r is -4 because -4 is between -7 and 3. Straightforward. Alright, so now we've got another one, same table. Explain why there must be value c, where c is between 1 and 3, so it's an interval, so that h prime of c is equal to -5. So if we're talking about h prime is in the interval, we're probably talking mean value theorem on this one. So let's look at what the mean value is. So if you remember, let's see, h of 1 was 3, and h of 3 was -7. Right? So that means the average value is going to be -7 minus 3 divided by, well, the difference between 3 and 1, and I'll just write it. So this is the average rate of change. -7 minus 3, that's -10. 3 minus 1, that's 2, so it's equal to -5. So if we have to explain, we have to say by mean value theorem, there must be some c where h prime at c is the average rate of change. From 1 to 3. Since that's 5, that means, or -5, that means h prime of c has to be -5 by mean value theorem. And that finishes it. Congratulations, everyone. Everyone did a pretty good job on this test. I just thought it might be good for everyone going forward to kind of just review, because all of these are relevant because they're all based on AP type questions. These are all things that I pillaged from actual AP tests, and so it wouldn't be out of source to see questions like this when you actually go take an AP test. So have a good day.